Well, welcome to the final session of this interesting and diverse conference. Our first speaker and keynote speaker this afternoon is Olfa Nasraoui, who's Associate Professor in the Department of Computer Science and Computer Engineering at the University of Louisville. She's the founding director of the Knowledge Discovery and Web Mining Lab at the university and received a PhD at the University of Missouri at Columbia. Her research activities include data mining, web mining, and computational intelligence. Her talk today is addressing two big data challenges: tracking and evaluating clusters of data streams and mining multi-source heterogeneous data.
Thank you. I'd like to start by thanking the organizers for inviting me to do this talk. And so I'm going to talk about two big data challenges, and this work is in collaboration with my PhD students and some visiting Fulbright scholars. So Bashir Hamash, Jafar bin Abdallah, Fabio Gonzalez is the visiting Fulbright scholar at Heterogeneous. And so this is an outline of my talk. I'm going to start by introducing the two big data challenges that I will talk about. And then I'll talk about, and that is clustering data streams and mining heterogeneous data. And then I'll go into the specific details for tracking and validating important clusters and data streams using some of the methods that we developed in our lab. And then the second axis is going to be mining multi-source heterogeneous data, and there I'm going to talk about two different approaches to do that. One is based on semi-supervised learning, and that's a new framework to cluster mixed data types. And the other one is based on non-negative matrix factorization for multimodal data mining. So I'm going to start with the big data, and I have here actually a snippet from the definition from the National Science Foundation Big Data solicitation this year, which is actually pretty new, and defines big data in this case as large, diverse, complex, longitudinal and or distributed data sets generated from instruments, sensors, internet transactions, email, video, click streams, and or all other digital sources available today and in the future. I don't know if I read everything, but it is actually a pretty big scope, I would say, and it really is actually bringing together what I consider different research areas. Actually, people have been typically working on maybe the diversity part or the complex part, the longitudinal part, separately from the other things. People have been working, of course, on video and click streams, but separately of all the other things. And then people have been working on data streams and so on, which is what they mean by the longitudinal data. And so the big data challenge actually includes all of these challenges, right? And it would be good to actually combine them. And the two big data challenges that I'm going to talk about today are the clustering of data streams. So this is unsupervised learning that does not assume the availability of any cluster labels, such as classes or categories, and so on. And the other thing is mining heterogeneous data. So when I say clustering data streams, what I mean is continuous arrival, right? And then data that is dynamic, evolving, noisy, and typically large. And examples of that abound: web user activities, which are also called click streams in some domains, network and system logs, Twitter streams, for example, or any kind of text streams, including web page content, emails, and so on. Okay, reviews, for example, customer reviews on e-commerce websites, sensor data, of course, and so on, right? And mining heterogeneous data, actually, what I'm talking about is mostly related to what you see here. It's actually known under different names. There is data with mixed types. For example, most of us at least have had experience with data that doesn't have the exact same type. Not every column or every feature is numerical, for example. So you might have some of the features or dimensions are numerical, some of them are categorical, part of the data is actually text, possibly free text, and some of the data may be transactions. And I will actually mention an example, a real-life example of that is if you look at movie ratings. Movie ratings are a very good example of heterogeneous data sets. So you have the ratings, right, of the users or customers on the movies, And then you have reviews, which are free text, right? And then you have the movie descriptions, actually, which are, they have several attributes, such as the movie genre, producers, the actors, and so on, and so on. Another name it might be known under is data with multiple views, a lot of times compacted into something called multi-view data mining. And multi-view data mining has mostly concentrated actually on supervised learning, where you actually have the class labels, right? And what I'm talking about today, though, is for unsupervised learning. Now it can arise, of course, from data that's coming from multiple sources, with or without mixed types, or data with multiple modalities. One of the very good examples of multiple modality data is if you look at the images on Flickr, for example, you have the visual content of the images, and then you have the tags, right? If you look on the web, then you have the visual content, and you have free text, and you have the hyperlink anchors, and you have sometimes tags also. So this kind of data sets actually arises a lot in real life. So I'm going to go ahead with the first topic in here, which is the clustering data streams. So here I'm going to present a technique for tracking and validating evolving clusters in data streams. So here what we want to do in clustering data streams, our goal is to extract knowledge in the form of patterns, specifically clusters, as a set of evolving clusters actually, in a continuous stream of data. And I already mentioned the examples of network activities, web logs, and so on. Now there are several challenges that arise in this context. One, of course, is the huge amounts of data, right? That furthermore arises constantly. Second of all, and specifically what we really notice, what we really address here is the evolution of the clusters. So of course, when you have data that is arriving continuously, it is really different from the clustering problem when we have a static data set. So we have clusters that can appear, clusters that can disappear, that can merge, split, or simply change actually in their metrics and so on. And the other challenge is there are, of course, strict time and memory constraints, because when the size of the data, stream is too big, you can't afford to store, of course, all the data, right, or even a big part of the data, and process it, and so on. And so a lot of times you have to process data only by seeing it only once. So you see something, you process it, update your model, do whatever you have to do, right, and then throw it away. Or possibly keep some of the data sets, some of the data points. So different approaches have addressed this challenge in different ways. What we do in our work is we actually see the data one time and that's it, right? There is no control over the order of data arrival, of course. You really have no control over which cluster the data is going to come from, and whether you have maybe the data from the whole cluster will come first, and then another cluster, and so on. So you really have no control over the data arrival. And I'll show you some examples in a minute. The outlier detection problem, which is already a challenging problem in all the data mining, in the entire data mining area, is even more challenging here. And one of the questions that arises is, if you see something that deviates, is it an outlier or is it actually the beginning of a new cluster or a new topic, for example? So you have to address that very delicately. Another thing which is challenging in the context of clustering, even for simple static data sets, is the validation. So validation means assessing the goodness of the cluster models that the data mining algorithm is discovering. In the case of course, they sometimes say that the validity of the clusters is in the eyes of the beholder also. So even two people may look at the data, even a simple two-dimensional data set, and disagree over the, how many clusters are in the data sets, for example, or whether something is noise or not. So to a certain degree, it can be subjective. Now, when we move to a data stream context, that problem becomes even more challenging, right? So trying to, what are you validating? Because the clusters themselves, remember, in a data stream, in a continuously arriving data stream, the clusters themselves are changing. right? So what you find at a certain time instant is not the same thing as what the cluster model is going to be later on and so on. So you actually have a continuously changing data set and a continuously changing cluster model, right? So how do you validate that? And what do you store, right? That, of course, depends on what the user or the customer wants, and so on. So what we have actually done here is trying to store as much as possible of the historics, basically archive the knowledge that is being discovered. Okay? Of course, deleting stuff that is always usually not problematic and something easy. Problem with storing everything, of course, because this is a data stream, right? Eventually, if you're storing continuously discovered model, right? Actually, you're creating another data stream, right? Is that clear? So your output will turn into another data stream. So that defeats the purpose of stream data mining. So one of the challenging problems is really knowing what to store and when, okay? And that is exactly the purpose of the first part of my presentation here. Now this is just an example. I'll show you later on. This is actually an experimental result, but if you look at the points in green, those are actually data points. This is a simple two-dimensional planar data set that just to illustrate. And it's showing you actually different snapshots, right, relative to the size of the entire stream. So in this case, this is the initial. Initially, you have points that are arriving this way, and then you have the points are moving and so on. And so initially, you may actually find just one cluster, just to illustrate the idea that the clusters themselves are actually changing, right? Because the data itself is changing, and then later on, you can see that really that cluster has actually split into 3 different clusters, right? So the challenge is, first of all, right, as these data points are arriving actually in one pass, right, one at a time, is estimating those clusters, right, their location, their scale, and so on, or any other metrics that depending on the clustering algorithm. And also trying to detect the change and characterize the change, right? What has really happened? I'm going to add something else, that according to stream clustering requirements, right, you're not allowed to really store the data, right? So one of the biggest challenges, actually, believe it or not, is if you want to find out here whether or not these are actually 3 clusters that have split from this first cluster right here and right here, right? That actually is challenging because you don't have the data, which is the evidence that supports your hypothesis, right? And so a lot of times what you have to do is actually compare cluster models. You're not comparing the data. Is that clear? So you're comparing the models, and actually you are using rules to try to make inferences on what is the most likely event that has happened. So even trying to determine whether clusters have merged or split or disappeared and so on, or there is also something called expansion and absorption and so on, is actually pretty delicate. This is another example that is showing merger, right? So clusters that are merging. In this case, the clusters are arriving. These are different snapshots, taken throughout the length of the stream. And you can see here the merging is gradual. You have 3 clusters and then 2, right? And then they all merge into 1. Again, here the thing is not only to do the clustering, right? Evolve with the evolution of the data, right? And then also characterize the change that has occurred over time, right? And storing that change and how you will actually store it and when, because you don't want to store everything at every instant, as I have said earlier. Now there are several methods for tracking cluster evolution. So this is more like a background review, and most of the methods actually divide the time axis into fixed length windows, and then they do the clustering within each time window, right? And then do their analysis by the intuitive approach of comparing the results at consecutive time windows. And you have what is called cluster-based evolution, where you find the clusters, right, in different time windows, and then find mappings between those clusters, right, in time ti and ti plus 1, for example, and then try to infer the changes based on those mappings. And then there's the distribution-based evolution, which is based on finding the deviations between the distributions over some kind of distribution that you estimate over the entire data set at the different snapshots. So the cluster-based evolution, basically, you find the clusters, right, at each time period ti. So time period ti is really essentially a window of data. And then typically the clusters there, you will either find them by, at the next time period, you recluster from scratch, which means you have new data, you do the clustering all over again, right? Or you use the previous clusters and you do that. There are even some methods that actually recluster the whole data set, which according to me do not even satisfy extreme clustering requirements. So the many-to-many mapping graph, which looks something like this, the columns here are different time periods, and the rows or the circles are different clusters. This is, of course, an oversimplified example. Right? So first you have to generate the many-to-many mapping graph between the clusters, and of course to map the clusters typically use a similarity, right, between every pair of clusters and different consecutive time points, right? And so some methods use the normalized sum of weights of the data points and the intersection between the clusters. So for example here, to know that these are mapped, you have to look at the supporting points, right? The data that belongs here, the data that belongs here, and you compute, simple intersection measures, set intersection, and use a threshold on that. There are methods that do that, and I'll talk about some of these advantages in a minute. And some others that measure the deviation between the cluster measurements, right, and so on. So at each, let's see, the transitions are reduced by analyzing the mapping graph plus using some additional rules, right, to infer whether something, two clusters have merged, for example, or one cluster has split, and so on. And as you can see, the rules are pretty intuitive, right, based on the similarity and threshold and so on. And there are two types of transitions typically that are inferred based on the mapping graph. So internal transitions are changes in the inherent cluster metrics that are attached to the data to the cluster. For example, the size of the cluster, the cardinality of the cluster, which is the number of points, or other things. External transitions typically refer to the interaction between the clusters. So, for example, that two clusters have merged, or that one cluster has split into two different clusters, right, in the next period, and so on. Those are called typically external. And so this is an example again of showing, again, this is at period T1, this is at period T2, and the orange is at period T3. In this case, this cluster has simply survived, and these two clusters have merged. So you see, it's actually a very simple and intuitive thing. What we need is really just to infer that, and infer that on the fly, and continuously, right, and without having to use the data, for example. Now, some of the disadvantages of these kind of approaches is most of them actually do reclustering of the data from scratch at each consecutive time period, so they don't obey the requirements of clustering data streams. And of course, this increases the memory and the time complexity and so on. The other thing, one of the actually biggest disadvantages, right, is the need to keep all the data points, right, or their identities, and/or actually, right. So keeping the data points, of course, defeats the purpose of stream clustering, stream data mining in general. If you have to use all the set of points that belong to the clusters from the previous time period, right, and then compare them with the set of points that belong to the cluster from the new time period, that assumes you are storing the points, which is against the requirements of stream mining. The other thing is you could, if you want, not store the data points, but give an index, an ID to each one of the data points, right? So you can, for example, store data identifiers. So I know which one is record number 1, number 2, and number 3, and keep track of that, right? And this again, remember, in the next time period, you're actually doing reclustering from scratch. So you're actually using those same data points that you have identified from the previous case. So it kind of defeats the purpose. But still, what I'm saying is that it will increase both the memory and the time complexity. The other disadvantage, big disadvantage, is the arbitrary division of the time domain into fixed interval length. Most of the techniques do this, and this makes the results very sensitive, of course, to the choice of that fixed interval length. It increases the risks of missing transitions, of course, especially if your window is very long, right? It's too big, bigger than it should be. It is wasteful if you have long, stable time periods in which nothing occurred, right? Because you're doing, again, the reclustering all over again, you're doing all the tracking and inference of what has happened and so on. But in the other way also, if your time periods, if your windows are very short, then you may actually be doing insufficient one. Okay, so so I'm gonna go ahead and skip the distribution-based evolution. Although the main disadvantages here is that the focus is on global change. Okay, so most of these techniques look at the global distribution, estimate and find changes. They don't look at cluster level changes, and typically they don't capture the internal and external changes, mainly because of the previous disadvantage actually. So I'm going to go ahead and present the stream dashboard framework, right, that we have developed. And it's actually a framework to mine the clusters, which means discover the clusters, track the clusters, right, and their changes, and also validate the clusters. And as you can see, actually, the reason why we validate is because we actually need to validate. That's something that we automatically do every time we cluster. We've done this in the many decades that I've been doing clustering. And when I moved to data streams, right, I still needed to validate. And that was actually an in and out with selling, very challenging problem. So there is more emphasis on mining the behavior of clusters rather than just detecting them. And as a matter of fact, I will show you that it's a modular approach, that you can actually use any online clustering algorithm that you wish within the framework. And because of that, it's actually generic, right? So you can use any clustering algorithm. And this is a flowchart which is on purpose, obviously amplifying the part that is actually tracking the behavior and doing the validation and so on. Okay? As you can see, the online clustering algorithm, the actual clustering of the data stream is only this part right here. If you can see the laser, right? It's the first oval, which is actually a small part, and we all know that some of us have been doing clustering for a long time. It's kind of underestimating the importance of clustering in a way, because clustering itself is a challenging problem. But I really wanted to do this because I'm devoting most of the time to talk about this. And so the data stream is the input, of course. The online clustering is continuously spitting out the output, which are the evolving cluster models, right, of any type. And the tracing model here is going to do the tracking and the validation, right, of the metrics which are output from the previous step. Right, and then I'll talk about the regression model that I noticed. What these are actually doing, we use regression literally to summarize and compress the change and the behavior that is occurring over time. And then there is a visualization and summarization model, which is optional at the end. And there is a high-level application here, which I put on the side. A lot of times we use the clusters, for example, to perform recommendations in a recommender system, right? So if you have that, so be it, that's very good. Actually, if you have that, then we can take the output of the application model, right? Whatever metrics we collect, and even fold it into the tracking and the behavior, okay? So the first component, right, which is the clustering algorithm right here, is actually any clustering algorithm, right, and it can be used provided that it satisfies the stream data mining requirements. And one of the first that has actually written about it was Barbara. So specifically, you need to be able to incrementally update the cluster model, right, with each new data point. You don't want to use all the previous data points every time that you have a new one. Right, and typically you want to be able to quantify the cluster characteristics using a set of properties. Typical example, let's say cluster centroid, right, the center of a cluster, the size of the cluster, maybe the cardinality of the cluster, and so on. What is not good typically to be done in stream clustering framework, although many people do it, is actually saving the partitions, which means what data points belong to what. You can do it because, as I said before, that requires at least saving the identifiers of the data. If not the data record, you need to be able to save the identifiers, which kind of creates actually another stream, or almost duplicates the stream. You're just compressing the dimensionality, actually. That's it. And there are several stream clustering algorithms that you're free to choose from. And what I'm going to show right here is actually the rhino streams, right? This one, which is the latecomer here, it's the newest one that we have. And it does incremental optimization of an objective function, so it's based on optimization. Basically, a cost function that's been maximized. It's actually the density of the clusters, and roughly speaking, intuitively, it's the number of points divided by the scale, but we actually use a measure as a proxy for the number of points. It's actually a soft arithmetic. There is no assumption of the number of clusters, which is needed in streams. Instead, we discover the clusters as we go, of course, subject to a maximum capacity. So, for example, if you say 100 clusters, that means you can't find more than 100 clusters, and then you need to have rules within your clustering framework to get rid of clusters when you have when you exceed your capacity. So it's kind of like based on survival of the fittest. Either survival of the fittest, right, or you use the time domain. So, for example, you may have rules that discard the oldest clusters, right, and you give preference to the new information. So, again, it depends what you want to do. It's resistance to unknown amounts of outliers, because this is actually rooted in robust statistics. It's actually in a very simple way. We use the Welsh estimator, right, for the weight, and we combine that with the Chebyshev test for outlier detection. So forgetting of old patterns is also allowed, right? Actually, we use this via weight decay. So we have a weight, which is shown here, a weight function, that decays with the distance of a point between a point and a cluster, right? And also with the time since the arrival of that point, sorry. And this is the density, so basically we maximize the density that I just mentioned, right? The density is the sum of the weights of the points within that cluster. This is the density for cluster I at time instant n, okay? So every time you get a new time point, you increment your time instance, okay? So this is based on simple incremental time instance. And sigma in this case is the scale, right, which is analogous to the variance, right, for Gaussian data. In this case, we just call it the scale. Again, most important thing is that the weights of points decrease with the distance, of course, from the cluster, and also decrease with the time or the age of the point. Other things we keep, of course, because we have this information, we're able to keep such things as the age of the cluster, basically when the cluster has emerged, right? And the other things we keep is also the age, the time since that cluster has last been updated, right? Or has actually seen the compatible data points, which are the beginning and the end. And so the simple algorithm in this case, we have for every new point xn arriving from the data stream, right? Which is ranging here x1, xj, xn, and so on. You find the distance, right? And from there the weight with respect to each existing cluster. If the point is an outlier, then you create a new cluster. Now remember, in streams there is no commitment, right? It's actually better to create more clusters, right, than to just rule it as an outlier, which is really just doesn't make sense, right, and ignore it. So you have to create a new cluster. And the Chebyshev test is actually given by the following bounds, right? Very simple. What's different people have used a lot of kind of tests. They've also used Chernoff bounds and so on. The Chebyshev test actually does not assume anything about the statistical distribution of the data. What it does assume is that you have a robust estimation of the scale of the clusters. That is the only assumption. And because we use the robust weights, right, we're able to do that. We actually update the scale also automatically, right? The incremental update equations can be derived simply by maximizing the following objective function. And we have an incremental update equation, as you can see here, for the centroids and for the scales. If you have a different model, you have to rework your update equations because your cost functions are going to change. For example, if you change your distance measures, right, typically you'll have to rework your update equations and rederive. And one more thing that we have, notice that each cluster is being optimized actually independent of the others. That's very, very important.
And that actually simplifies the objective function a lot. If you look at the objective function, it is multimodal, but typically every cluster will create a local mode, right? So when you're close to a specific cluster, right, you have actually a well-behaved objective function that you can actually use these local updates and converge and get something new. The other thing is we overspecify the number of clusters. So we actually prefer many small microclusters, which makes this optimization much easier instead. And after this, of course, we do a test for merging, right, and extension and splitting of the clusters based on the Chebyshev compatibility test. This one here compares a point to a cluster. When we do, for example, merging, we compare a cluster to a cluster. So we actually compare the centroids as proxies to the data points. We remove the weak clusters based on a threshold value over their density, right? We also protect the new clusters by giving them a grace period in terms of the time, and that is why we keep the age and so on. And that way we are able to distinguish between outliers and new clusters that emerge. The Chebyshev bound, as I showed you before, this equation actually is equivalent to this one. This is the way that you would probably see it in statistics books, but you can take the exponential on both sides to get something that looks like the weights. The reason why we do that is to get a condition on the weights, which is sometimes more intuitive, right, for people who work in robust statistics. The merging, right, this actually is coming straight from the Chebyshev bounds, these conditions. This is for testing whether clusters are compatible enough to be merged. The splitting actually happens really naturally, because what happens is that as new points typically gradually evolve outside the cluster influence area, which is defined by the sigma and actually by the Chebyshev bound itself as a proxy, and eventually a new cluster will be created, right? So it's actually a natural byproduct of this. We don't have to do anything special. What is hard, though, is actually inferring that splitting has occurred or merging has occurred and where. In the future, okay? This is just an example here showing one-pass clustering for a data set, which is shown here. It's actually a noisy data set, and here what we do is we don't show the noise that is detected. If the noise has been detected by the stream clustering algorithm, the noise then is deleted, right? It's not shown, and these are the clusters, and they're actually colored with different colors. This is just a comparison with an algorithm called incremental DB scan, which is actually a pretty good algorithm. It's actually an unfair comparison because incremental DB scan really uses the whole data set and reclusters. So, but it is still using incremental updates and so on. And as you can see here, we do a good job of finding the clusters, right, and detecting the noise and eliminating it. And at the same time, this is actually doing one pass over the data point, which means every point is used exactly once. And these are certain validity measures on the previous dataset clusters. And what you see here is different dataset variations. We did all kinds of things like the initialization, how much noise is contained. So we did several controlled experiments, also changing the order of arrival. The order of arrival of the data points is extremely important. So whether it's random, completely random, or certain clusters before, or 3 clusters at the same time, and then 1, and so on. So we did several controlled experiments. This is showing that you can find the number of clusters correctly, and this is the C-wet index, which is a validity metric that actually measures the goodness of the clusters in terms of how compact they are within and how separated they are from the other clusters. This is, of course, comparing to deep incremental DB scan. This is actually the same picture that I showed you, but showing the results, right? So the circle is actually, that's the cluster that was discovered at when that particular snapshot was taken, right? And the data we're showing all the data since time 0. And here we're showing the splitting and so on, and this is the merging. This is for a document or text data set, okay? And we had the categories, so we were able to validate the clusters. We did not use the cluster labels, of course. We processed the documents one at a time and so on, but we were able to still verify that the clusters are actually pretty pure. Remember, this is a one-pass framework. Remember, also the labels themselves are not perfect. As anyone that worked with labeled text data, that people disagree on whether a document is of this class or that class, is usually overlap, there is noise, and so on. Now the next component, right, of stream dashboard is tracer. So that what I showed you there is just the clustering algorithm. This is tracer, which takes the output of the clustering algorithm and does something with it. So specifically tracking and validating and so on. So this framework actually builds and maintains summarizing regression models of the metrics, for example, the scale, right, or the density, or any validity measure that you wish. And it uses regression to do that. And furthermore, it detects time periods of major changes, which we call the milestones. And so it builds behavioral profile actually for each one of the clusters that summarizes how that cluster has evolved and what it has seen and so on through time. So it looks something like this. And we use linear regression. It's very simple to extend this to quadratic or whatever you wish. But we thought that linear regression not only is simple, of course, more compact, but specifically also allows us to find the changes, the milestones easier. Because if you have complex models, right, then you start looking for inflection points and stuff like that. So these points here, actually, we divided the time axis into several windows, right, which are smaller than what we expect when we found the milestones. And then we model each metric's values over time using a regression line, a linear regression model. And then we compare consecutive regression models. So in other words, what we do is we compare regression models, right, to infer the change in the trend, right? And we also compare the cluster centroids if we want to find whether the clusters are the same or something like that. So the cluster metrics, they can be generic, right? For example, cardinality or number of points, or algorithm specific. If you go within certain clustering algorithms, they actually specify certain things. Or it could be a validity measure. For example, the silhouette coefficient that I mentioned before, if you want. But preferably you want a validity measure that is computable in an incremental manner, right? To make it fast. Otherwise it defeats the purpose of everything. And typically we use two generic cluster descriptors, the scale and the cardinality, and one validity metric, which is density. It's also the same as the optimization criterion. And other metrics can be computed if you're using different things. So delta regression, right, is the regression window size. And typically, as I said, we build a linear regression model for each time period, right? And the comparison is actually based on the angle difference between two lines. Is very simple, right, to find that. And then the next thing that you do is also characterize the time of time, whether we have a stable, for example, stable line, right, there is no change, or whether we have a steady increase or decrease and so on. If we have like fast acceleration, right, in that increase, then typically that will generate a new regression model, right? Then we will have milestone, and we will call it that, and start the regression modeling from anew. The other thing that we do also is we infer the merging and the splitting, and merging and splitting actually occur naturally, as I've shown you before in the clusters, right? The thing is, when you merge clusters, it's very simple, right? You combine their parameters or the models, right? And when they split, they split. But when we're doing this regression modeling here, we have to take extra care to actually merge those. So that's what this slide is showing here. So we make sure and we store, we only combine, of course, the lines that fit each other's models. So we use confidence interval tests and so on. The merging and the splitting, again, I want to specify, record the data is not stored, right? And the first component clustering, actually, because it could be something we don't own. It could be a black box that's just spitting out certain metrics. So it's not really trivial or evident that you actually know that certain two clusters have merged or clusters. Is that clear? And so in some cases, you actually have to infer it in retrospect. And so that's what this is also talking about. So there are rules that we use. Actually, the rules can be either hand-coded or they can be learned based on training and testing, right? Based on lots of lines. And the actual whole framework is very simple. So for each point, you perform the online clustering, whatever algorithm you have, you update the clustering model and the metric values. If you're capturing validity measures, for example, if you reach the window, right, the regression window size, you call tracer, right? So you try to build the regression lines, right? Apply the rules and so on. If two clusters are merged, you merge their behavior from the dot on tracer. Otherwise, if one cluster splits, you inherit its behavior, and so on. The two clusters, right? That way, you keep the history of what happened to the two clusters that split from their parent, right? You inherit that from the parent, and so on. Time complexity is linear in the number of metrics and the number of clusters. Remember, we don't involve the data dimensionality. We don't store actually the data at all, not even the identifiers. The memory complexity also is linear in the number of clusters, metrics, and milestones. And the number of milestones is much less than if you were to actually split the whole time into fixed interval windows, which is the first method that I mentioned. The other, most other people do. Compared to cluster-based evolution, we do adaptation rather than reclustering from scratch, right? So we validate the clusters on the fly. It doesn't need to store or process the data points or the identifiers, and also captures local evolution. So this is just an example that actually shows what typical tracer output for, in this case, the cardinality. For each cluster, each different column is a different cluster. And actually what this has is the continuous lines are the output models, right? And the dashed are the actual metric values, right? For example, cardinality. You can really extend this to any validity measure that you want. And obviously the modeling is pretty accurate. Remember, you do the milestone detection, right? You have to do that to detect, whether or not to merge two regression lines or not, for example. So the fact that when you superimpose them, you see that perfect reconstruction, basically, that the milestones are actually detected well. If you don't detect the milestones well, you will not have something which is good. Okay? So you want the fewest milestones that allow you a good reconstruction of the history. Basically, that's what we're trying to do actually here. We're kind of guessing, not the future, but we're guessing the history. That's exactly what we're doing of the cluster evolution. This is the density, which is a very good validity measure of how good each cluster is. Actually, this tells you more than just what happened, but it tells you whether your clustering algorithm in component number 1 is successful or not. So you can use this in the future. We plan to close the loop, hopefully use this to try to improve the choice of the parameters, for example, that are being used in the clustering algorithm and so on. This is for a text dataset, for the routers dataset. This is showing, again, same thing for cardinality and scale, different colors for, in this case, showing one cluster that where you have first the red points appear, then the blue on the periphery, and then the green. Again, the explanations are here. The slides will be posted. So I'm going to try to skip. This is the splitting again and showing how the metrics evolve with, how much time do I have? I think I have to wrap it up very quickly, go to the next section, I think. So this is showing the validities that you get with splitting, and this is showing the quality of the milestones and regression models. So in this case, really what this is showing you, how accurate is the milestone detection, very simply. And really the only way to actually do this is to do controlled experiments. And there are several, actually many controlled experiments with this. This is from one of them. And this is showing 75% recall, 50% precision. The actual regression model quality, right, is also decent. This is similar to the other graphs that I've shown you. And this is showing the memory complexity, specifically the difference between the tracer models, like the output of our trend analysis and so on, and versus actually saving them in every fixed interval width. Right, which if you did not detect the milestones, right, what would happen? And it shows, of course, as the window size increases, right, there is less change. If the window size is small for the other methods, right, then we have a lot of savings. And there is a lot of ongoing work, and some of it will spill into the future, including specifically mining tweets. What we're doing is actually getting the tweets, clustering them, and adding an opinion finding or sentiment analysis layer to that. So I'm going to skip over the next stage. This is just an example. So mining multi-source heterogeneous data with semi-supervised learning. So I'll give you the idea very quickly. I think I already motivated that before. So you may have data that has different representations, diverse representations of the data. You may, for example, have comments, reviews, annotations, and so on. And what you want is you want to actually use the different parts of the data to help each other, if possible, find a better clustering. So this is a collaborative framework, actually. Or it could be data coming from different sources, of course. Actually, that would be another thing. So the first, and I'm going to skip over typically what people do typically is they take the mixed type of data and they will. This is an example, by the way, right? So we have numerical and categorical, let's say, right? You have one database here, and you have different types of data, and typically a lot of people do the conversion method because it's just very, very easy. It's the easiest, most trivial way, and you will convert either to everything categorical or everything to numerical. The most common way is to actually do it with numerical, except if you're classifying decision trees and so on, and then use a clustering algorithm for the target domain, whatever you convert it to. So the limitation of the conversion approach, there are a lot of problems. A lot of times you actually create artifacts, right? Everybody that has discretized data knows that if you discretize in the wrong way, you will actually create wrong clusters. And that's something very simple actually to show. And other kinds of artifacts. The other thing actually is sometimes, especially with text data and clickstream data, and social network data, graph data, there has been already a wealth of really good algorithms that have been developed over the last decades, specifically for those kinds of data, right? So really converting everything in one bunch and feeding it through one clustering algorithm may not always be the best thing. Sometimes it's good, right? But sometimes it's not. So what this allows you to do is actually take advantage or exploit the best algorithm that exists out there, right, for that specific part of the data. If you have a view which is a social graph, you can use, for example, kernel clustering and so on. If you have a view which is categorical, you can use the ROC algorithm, which is a very well-known algorithm, right? If you have a view which is text, you can use a text mining algorithm, spherical k-means or something like that, or Dirichlet weighted allocation and so on. So that's what we're trying to do. So the other approach is you use an algorithm for mixed types. There are algorithms that simply mix the types, and the way they do it most of the time is they either do the updates in parallel, separate from each other, right, or they compute one combined distance measure, right, and use it. And there are other fusion ensembles. The most common ones, I know that some of you may have heard of these, are clustering ensembles. These are good not just for mixed type. These are good especially if you have several sensors and so on. You can use this also, right? So you can cluster each domain, right? Or you use different clustering algorithms, and usually the end with clustering ensembles is you have to combine them. That's another approach, okay? The other approach is something called multi-view clustering, which has been used especially for graphs, right? People that work with kernels do this a lot. So one of the things is you want to combine two graphs. This is only good, by the way, for combining graphs with graphs. This is not about really diverse kinds of data. So if you have two graphs, right, you have hyperlinks and you have the friends graph, right, for example, something like that. So then you can use, for example, do a Markov random walk to combine the two graphs, for example, right? You can do kernel addition if you're using kernel clustering, right, and so on. Or you can actually find two different clusterings, right, cluster models from each graph, each kernel, and then combine the results, and so on. So the proposed semi-supervised framework doesn't do any of that. Actually, what we do is we cheat, right? What we try to do is we do the clustering in parallel in each domain or in each view or in each source. And then we try to detect which clusters from each specific source is better, right? So we try to compare with validity measures, of course. The clusters which are good, which are detected to be good, right? We use the seeds from those clusters, the points that are the best representatives, which are all of these things, by the way, are typically not that hard to find, right? And you can do this fast. And then use those to guide the clustering in the other domain. Is that clear? Right? So it's a collaborative framework. It is really based on trial and error. It's an iterative way. And really what I do is actually, I consider it as really as a new kind of learning. It is not supervised, of course. We don't have the labels, right? So it's not unsupervised completely because we're using a semi-supervised learning framework. And really what this is actually, this is a newly funded project actually, funded by the NSF. And the idea here is really to explore whether semi-supervised learning as a framework can be used to combine, right, not really crisp labels, not known labels that are given by humans, right, but labels that we can infer, right, from other clustering algorithms. And partial labels, of course. This is actually very flexible because you can have clusters, data from different sources, and some of the data is actually missing attributes. Even some of the data is altogether missing. It doesn't matter, right? You can have noise. You can use different algorithms specifically designed for each part of the data. So it gives you an amazing flexibility and power in choice. And again, this is just a big flowchart showing, for example, you have a mixed data set. This is, of course, a simple one. I'm not showing something that has, for example, a graph or something like that. And you take the different types, right? And you can use a specialized, well-performing algorithm that has been proven for that specific domain, right? And then the main thing here that we do that is new is actually the collaboration between the partial outputs of certain algorithms that guide each other and so on. And of course, you have results. There are several things that can happen. The easiest thing is each algorithm will give you a result. And then the next thing is to combine. This is hot off the press, so I can show you a lot of good results, lot of results. But this is a flowchart showing you again. So you start with an initialization. And typically here, let's say we have just two components, just to simplify and have something that fits in the slide. So you take random initial seeds, run algorithm 1, algorithm 2, then you find the best seeds combinations. You use the best seeds to, depending on which algorithm, right, found better seeds, you use those best seeds to seed the other algorithm, right, and so on. And this is iterative, as you can see, right, you get the best seeds in the next iteration, or k iterations. So all of these, again, subject to research and experimentation, and you keep going, basically. Right? And the final thing is typically you have actually different results, right? And you can either select from those, right? Or you can combine those, and there is a certain validation steps. I'm going to skip over this. And I'm going to show you just simple results here for example, the adult data set, which is a machine learning, UCI machine learning data set, and showing here that you have the supervised algorithm, the semi-supervised framework. This is if you convert everything either to numerical or to categorical, right? This is if you take the numerical by itself and take the categorical by itself, and you find it. Okay, so in this case, what we're showing is actually several validity measures. In the cases where we actually have labels, we're able to go beyond that and compute what is called external validity measures, such as the purity and entropy of NMI. And in this case, we get something better for the semi-supervised. What this means here, why we have two columns, remember we have different algorithms that are running on each part of the data. So you actually have two results, right? So you can choose one of those or you can combine them. We worked also on the combination, but I don't have it here. This is the credit card data set, which also has part of the attributes are categorical, part are numerical. And here we do get also better results based on all the validity measures. We do not claim that this is something that always will give you better results. Of course, sometimes you convert and even get better, right? What we claim is that this is an alternative learning framework to accomplish that, right? And the best thing would be for the next step is finding out when it is actually good to use this framework and do the combination like this, right? And when it's not good, right? Or everything is performing the same, you just leave it alone. So that's the idea. How much time do I have? Am I out of time? Almost, yeah. So then the other thing that I'll just skip over is a completely different thing. It's based on non-negative matrix factorization, but essentially it's also for combining different modalities. And the idea is to take a distance, data matrix and factor it, in this case, into two smaller matrices. And these are the latent factors, right? They're also called the latent concepts. You can also treat them as clusters if you want. There is a slight difference between, for example, using SVD and using non-negative matrix factorization, because the latent factors are kind of like clusters, but they are allowed to overlap. That's one of the main advantages, actually, over SVD, and so on. And the H is a combination weight matrix, which can be considered as the memberships, the cluster memberships or assignments. And there are several objective functions you can use. So some of you may be familiar with that, so I'm going to skip over that. These are the update equations, right? Pretty simple. I think everyone here knows how to do that. And what we use this is for multiple sources of data. For example, specifically we use it for images and tags. We also use it for images and text, and ratings and text, and so on. So I'm going to skip to, so the main idea behind this, right, is you may have the visual features, let's say the text features, right, for a specific data set. What the non-negative matrix factorization does is actually builds a latent space or a hidden space that captures the semantics between the different modalities, right? Once you have that latent space that actually captures both modalities, it's actually very powerful, because what it allows you to do is it allows you to retrieve the closest data records given only part of the information. If you only have text, you can get something. If you only have images, you can get something. And you can also build better predictive models, for example, recommender systems and so on. You can use it for image retrieval. You can also use it for automatic annotation. So if you only have images, you have a picture here that only has visual features, right? You can compute simple similarity measures, k-nearest neighbors kind of similarity measures in the latent space, and come up with annotations automatically, which are text in this case. So that's the idea. The main thing that is new that we did here, right, is the asymmetric part. Okay, the mixed non-negative matrix factorization, various people have done it in really different ways around the same people. But what we did is something called asymmetric non-negative matrix factorization, which works in 2 steps. Most of the techniques, they work in 1 step. They take the matrix and just factorize it. Let's see, where is it? Right here, right, in 1 step that gives you the latent space. What we did is use 2 steps, right? In the first factorization, we use only the text part. Remember, these are the features, right? So we ignore the visual features, especially for images, okay? So we use only the text features, right? And find the factorization that gives us the text factors. Then we fix those, right? And folding the image part, right? And perform a second step factorization, which is usually easier and faster because part of the factors are fixed. And then find the final latent space that combines them, and that looks, just like what you get from the other one. But what we have found through our experiments, through multiple runs and several data sets, is that actually using the text for this particular case of annotated images first to guide the factorization in the second step actually gives you tremendous improvements over using just one step factorization. So I'm going to go to the summary. Hopefully you'll get the chance to look at the slides and see all the nice results and the examples of the automatic annotation and so on. Do you want me to go over that? Oh, something else that we're working on also, again, because of the different modalities. You can look at that in the slides, right, using something called the beta divergence and optimizing the beta for different modalities. So just to summarize, basically what I talked about, if you remember, first part was discovering clusters and data streams, right? And detecting and measuring and characterizing the evolution in retrospect and so on, right? And several applications actually can provide metrics and that you can fold into that second component. So the main thing here is trying to summarize the evolution trends which are being monitored and computed online. right? That's called the stream dashboard. The next part I talk about is the heterogeneous or mixed type, or multiple modality or multiple data sets. And the semi-supervised framework basically allows different clustering algorithms to collaborate to arrive at better results. And the non-negative matrix factorization does it in a slightly different way by actually discovering latent space first and then working within that space and doing whatever data mining you want to do. And there are a lot of ongoing and future work. I think I mentioned some of it before, sorry. And so that's it. Thank you so much for paying attention.
We have time for a few questions, and there will be slides with lots more information to look at if you've seen. So,
and the video.
Thanks for the talk. One question about the clustering piece was, how does it work in a distributed environment? And is there
the second one or the first one?
The first part, the clustering?
The first part, the stream data clustering,
yeah,
the Rhino stream and stream dashboard, we actually don't do that in a distributed framework, but it is amenable actually to a distributed framework. If you use any of the distributed frameworks that exist out there,
what sort of overhead would be added by inter-process communication between these servers? Because each server only gets a partial view of the world, right? And so the clusters are going to be quite distinct and almost incomplete in their view of the world.
So I think what you might be talking about is actually the semi-supervised learning, right? The collaborative framework, because you have different sources. Like if the different algorithms are residing in different places, right, and they're running, then the overhead would be whatever information you're passing in between the different sources.
In my scenario, the underlying algorithm is the same. Let's just assume it's a k-means clustering. And we're trying to cluster users and recommendation for movies, right? Just trying to detect like users, right? Similar users with similar kind of watched movies. And so you have this layer of a distributed environment where you have multiple servers. Each gets a different data stream. How would you kind of communicate?
Yeah, the main overhead I would basically see is, first of all, getting the validities from each source, right? That's local, that's not a problem. But comparing them, right, assumes that there is certain exchange. So knowing which clusters are better, right? And then actually sending the information. If you're going to send a seed, for example. And the other thing we mentioned, I don't have it here, but we also did imposing constraints in a semi-supervised framework. Then you actually want to send those constraints, which are pairwise constraints. So still you're not, of course, sending the entire data set, right? But you're sending, certain things, either seeds or constraints, right?
Yeah, maybe we can continue the discussion. There's quite a long break coming up. It brings us to the next speaker.
So I'm going to start with the big data, and I have here actually a snippet from the definition from the National Science Foundation big data solicitation this year, which is actually pretty new, and defines big data in this case as large, diverse, complex, longitudinal and or distributed data sets generated from instruments, sensors, internet transactions, email, video, click streams, and or all other digital sources available today and in the future. I don't know if I read everything, but it is actually a pretty big scope, I would say, and it really is actually bringing together what I consider different research areas. Actually, people have been typically working on maybe the diversity part or the complex part, the longitudinal part, separately from the other things. People have been working, of course, on video and click streams, but separately of all the other things. And then people have been working on data streams and so on, which is what they mean by the longitudinal data. And so the big data challenge actually includes all of these challenges, right? And it would be good to actually combine them And the two big data challenges that I'm going to talk about today are the clustering of data streams. So this is unsupervised learning that does not assume the availability of any cluster labels, such as classes or categories, and so on. And the other thing is mining heterogeneous data. So when I say clustering data streams, what I mean is continuous arrival, right? And then data that is dynamic, evolving, noisy, and typically large. And examples of that abound: web user activities, which are also called click streams in some domains, network and system logs, Twitter streams, for example, or any kind of text streams, including web page content, emails, and so on. Okay, reviews, for example, customer reviews on e-commerce websites, sensor data, of course, and so on, right? And mining heterogeneous data, actually, what I'm talking about is mostly related to what you see here. It's actually known under different names. There is data with mixed types. For example, most of us at least, have had experience with data that doesn't have the exact same type. Not every column or every feature is numerical, for example. So you might have some of the features or dimensions are numerical, some of them are categorical, part of the data is actually text, possibly free text, and some of the data may be transactions. And I will actually mention an example, a real-life example of that is if you look at movie ratings. Movie ratings are a very good example of heterogeneous data sets. So you have the ratings, right, of the users or the customers on the movies, and then you can have reviews, which are free text, right, and then you have the movie descriptions, actually, which are, they have several attributes, such as the movie genre, producers, the actors, and so on, and so on. Another name it might be known under is data with multiple views, a lot of times compacted into something called multi-view data mining. And multi-view data mining has mostly concentrated actually on supervised learning, where you actually have the class labels, right? And what I'm talking about today, though, is for unsupervised learning. Now it can arise, of course, from data that's
Well, welcome to the final session of this interesting and diverse conference. Our first speaker and keynote speaker this afternoon is Olfa Nasraoui, who's Associate Professor in the Department of Computer Science and Computer Engineering at the University of Louisville. She's the founding director of the Knowledge Discovery and Web Mining Lab at the university, and received a PhD from the University of Missouri at Columbia. Her research activities include data mining, web mining, and computational intelligence. Her talk today is addressing two big data challenges: tracking and evaluating clusters of data streams, and mining multi-source heterogeneous data.
Thank you. I'd like to start by thanking the organizers for inviting me to do this talk. And so I'm going to talk about two big data challenges, and this work is in collaboration with my PhD students and some visiting Fulbright scholars. So Bashir Hamash, Jafar bin Abdallah, Fabio Gonzalez is the visiting Fulbright scholar and actually Abdullah. And so this is an outline of my talk. I'm going to start by introducing the two big data challenges that I will talk about. And then I'll talk about, and that is clustering data streams and mining heterogeneous data. And then I'll go into the specific details for tracking and validating important clusters and data streams using some of the methods that we developed in our lab. And then the second axis is going to be mining multi-source heterogeneous data, and there I'm going to talk about two different approaches to do that. One is based on supervised learning, and that's a new framework to cluster mixed data types. And the other one is based on non-negative matrix factorization for multimodal data mining. It's coming from multiple sources, with or without mixed types, or data with multiple modalities. One of the very good examples of multiple modality data is if you look at the images on Flickr, for example, you have the visual content of the images, and then you have the tags, right? If you look on the web, then you have the visual content, and you have free text, and you have the hyperlink anchors, and you have sometimes tags also. So this kind of data sets actually arises a lot in the real life. So I'm going to go ahead with the first topic in here, which is the clustering data streams. So here I'm going to present a technique for tracking and validating evolving clusters of data streams. So here what we want to do in clustering data streams, our goal is to extract knowledge in the form of patterns, specifically clusters, as a set of evolving clusters actually, in a continuous stream of data. And I already mentioned the examples of network activities, web logs, and so on. Now there are several challenges that arise in this context. One, of course, is the huge amounts of data, right, that furthermore arise constantly. Second of all, and specifically what we really notice, what we really address here is the evolution of the clusters. So of course, when you have data that is arriving continuously, it is really different from the clustering problem when we have a static data set. So we have clusters that can appear, clusters that can disappear, that can merge, split, or simply change actually in their metrics and so on. And the other challenge is there are of course strict time and memory constraints, because when the size of the data stream is too big, you can't afford to store, of course, all the data, right, or even a big part of the data, and process it and so on. And so a lot of times you have to process data only by seeing it only once. So you see something, you process it, update your model, do whatever you have to do, right, and then throw it away. Or possibly keep some of the data sets, some of the data points. So different approaches have addressed this challenge in different ways. What we do in our work is we actually see the data one time and that's it, right? There is no control over the order of data arrival, of course. You really have no control over which cluster the data is going to come from, and whether you have maybe the data from the whole cluster will come first, and then another cluster, and so on. So you really have no control over the data arrival. And I'll show you some examples in a minute. The outlier detection problem, which is already a challenging problem in all the data mining, in the entire data mining area, is even more challenging here. And one of the questions that arises is, if you see something that deviates, is it an outlier or is it actually the beginning of a new cluster or a new topic, for example? So you have to address that very delicately. Another thing which is challenging in the context of clustering, even for simple static data sets, is the validation. So validation means assessing the goodness of the cluster models that the data mining algorithm is discovering. In the case of course, they sometimes say that the validity of the clusters is in the eyes of the beholder also. So even